Well, we had a look at parallel resistance, and now what we're going to have a look at is DC parallel resistance circuit. We basically put together a circuit. Our supply voltage is 9 volts, R1 is 220 ohms, R2 1.5k, and R3 is 68k. Electron flow that we're using, as you can see by the arrows, as opposed to conventional flow. Now the first thing I did was just to do the calculations for the total resistance, and you've seen that formula before. Then we basically go 1 over each of the resistors as we've got laid out there. Then we find the conductance of each resistor, so you've got 1 over right conductance, and then we get the total conductance by adding these three up, and we've got 1 over right total conductance there, and then if you invert that again you're back to resistance, which is 191 ohms. So the total resistance of all three in parallel is equal to 191 ohms. Now the next thing I did was just to find out the total current, and I did this just to do it as a comparison. So the total current is the supply voltage, which is V, 9 volts, by the total resistance, which you can see there is 191 ohms, and if you divide that out you get 47.12 milliamps approximately. Now there are some rounding errors through all this, because of the type of calculations that you get. From that point, what we did is find each of the currents through the branches. Now remember, we said that in a parallel circuit, right, your total resistance is always going to be less than the smallest resistance in the circuit, and you can see that's exactly what happened here. And obviously, depending on the resistance, this one will be the larger current, the medium, and the lower current. And you can see that represented here. So if we find I1, so the supply voltage divided by R1, you can see we've got that there, and we end up with 40.91 milliamps. I2, supply voltage divided by R2, as is depicted here, and you end up with 6 milliamps. And then I3, supply voltage divided by R3, depicted here, which is 9 over 68k, and you end up with 132.353 microamps. I just left that a bit longer so we didn't get too much rounding error. If I add these three up, our total current from the calculations and taking in consideration rounding errors is 47.04 milliamps, which is pretty close to 47.12 milliamps. And you can see that this parallel circuit is a current divider. So the current using electron flow is leaving the negative terminal, travelling along, it meets this intersection here. Some of the current goes up through here, which is the 40.91 milliamps, moves along, more current travels up through here, which is the 6 milliamps, and finally, being the larger resistor, I3 is 132.353 microamps. If you add all those up, right, so it's all travelling through, it's all recombining up the top here, and your total current coming back in and also leaving is 47.12 milliamps theoretically, and you saw here that we got 47.84 just through calculation. So the first thing I'm doing here is just getting our lead resistance. You can see there we've got 0.3 of an ohm for our lead resistance, so that needs to be deducted off whatever resistance measurement we get. So here's our circuit here. We've got 220 ohms, 1.5k and 68k. And if we take our overall resistance measurement, and just let the meter settle down a bit, you can see we've got 191.3, well 0.2, but we'll call it 191, and that's pretty close to what we calculated with reference to the three resistors in parallel. So what I'm going to check here is the actual battery. It's a 9 volt battery, and you can see we get 9.27 volts, so just slightly over 9 volts. So that will also give us a slightly different result. So what I've done is just hooked up the supply, which is just a 9 volt battery. You can go to all the expense of getting a power supply, but for simple work like this, a 9 volt battery is going to do the same thing. So what we're going to do now is just measure the current, and this will be the total current. So again, making sure your leads negative to negative, and the positive lead to the more positive side. You can see here that our reading is 46.7 milliamps. Alright, so taking all factors into account, you can see here that with the battery under load, the voltage drops. You've got 8.95. Just traps to be aware of, unless you've got a consistent right voltage source. Small batteries like that, will drop down in voltage, under load. This is the total current measured compared to, your total current calculated. And you can see here that we've allowed for a battery voltage change at a point of time, and it was 8.96. We know that the measured resistance was about 191, so that basically gives us 46.9 milliamps, which comes very close to the calculated values, which is 47 or 47.12. So we're not far off the ballpark, even though the 9 volt battery actually drops slightly below 9 volts, as you can see here. Now the next thing I'm going to have a look at is power consumption, and we're just going to do our calculations based on a 9 volt battery and the current that should be flowing. So what I've done here is just gone through and done the power calculations. The first one I did was total power. So what we've used here is supply voltage and the total current. And if you work that out, you end up with 424.1 milliwatts of power being dissipated. Then I did it for each of the branches. So power at R1, R2, R3, and this time I used power equals V squared over R. It's just an easy calculation with the information that we've got here, and that's just basically supply voltage squared divided by your resistance. And as you can see, we get for the power dissipated at R1 is 368.2 milliwatts, R2 is 54, and R3 1.19 milliwatts. If you add all that up, that's these three, you end up with 423.39 approximate, which is pretty close to 424.1 milliwatts based on a 9 volt supply and a 47.12 milliamps total current. Now the important part with reference to working out your powers is what rating of resistors are you going to use for each of these branches. You can see here that we've got 368.2 milliwatts of power. So a quarter watt resistor in this situation is going to be too low, and you probably have to go to a slightly higher value. Whereas a quarter watt resistor in R2 and R3 would be fine, because your power consumption is only 54 milliwatts. But the other thing that you've got to be careful of is that if you get a breakdown in one of the resistors in the branch, then you're going to have a change of current flow through the system, and that could be an interesting thing to work out. Say, if the 68k broke down, or the 1.5 broke down, or the 220. So I'm talking about a breakdown as an open circuited. Obviously a short circuit, is going to cause major problems, but an open circuit, within the branches can and will change your current flow when you're looking at IT. So what we're going to do here is just have a look at conductance. And as we mentioned earlier, 1 over resistance gives you these values here, and these values, 4.55 times 10 to the negative 3, is what's known as conductance, which the symbol is G. So conductance equals 1 over resistance. So what conductance is an expression of the ease with which electric current flows through materials like metals or non-metals, and it's either represented in Siemens or mhos, and I'll explain that in a minute. So what I've done here is just use an example from our equation. We've got 4.55 times 10 to the negative 3. And how we got that, right, conductance equals 1 over resistance, so the resistance is 220 ohms. That gives us a result of 4.55 times 10 to the negative 3, either Siemens or mhos. Now, there's a little bit of controversy as to which is used, and what we're talking about here is that the older measurement was in mhos, which is just ohms backwards. The current is Siemens, but when you put the letter S down there in certain situations, it could be seconds. So it gets very confusing as to whether it's Siemens you're talking about or seconds in certain applications. So you'll quite often see either S being used, or in some applications you may see the older system mhos being used. So if you have a look at this equation here, you can see that we get different values from the lowest resistance to the highest resistance, and your conductance varies accordingly. Once we've got that added up, we end up with this result, which is the total of these three, as we explained before. And now what you're doing is reverting it back to resistance. So 1 over conductance will bring you back to resistance.